Hello, students. We're getting into section 11.3. Now, this one is more about angles. They are, to be honest, this one is pretty cool. And to be honest, this is where we finally get to this is the baseline for a lot of what we're going to be doing for the rest of the term. So chiseling out, yes, there's some new terminology, but let's take a look at what the Common Core has to say about this. By the time they hit the 7th grade, students are going to be finding facts about supplementary, complementary. We already talked about those. Supplementary straight line. Straight lines are 180 degrees. Complementary. Oh, you look so nice. That is the right thing to do. Right angle. Complementary. And I know it's spelled different, but go with me. Vertical and adjacent angles in multi-step problem to write and solve simple equations for an unknown angle. In order to solve equations about an unknown angle, we have to know some facts about them. So let's take a look at what we have here. All right. So we start off with two lines intersecting. When you do have two lines intersecting, you will form four angles. And what's great about these angles is that they kind of look very similar. As you can see here, it looks like angles 1 and 3 look very, very similar. What we're learning in geometry is that just because it looks that way doesn't mean it has to be that way. We want to be able to prove this. So one of the first things we're going to do is we're going to prove something about vertical angles. All right. Now, just so we're clear, the name vertical angles is just describing angles that are kind of on opposite sides of where the lines intersect. So 1 and 3 are vertical angles, and 2 and 4 would also be called vertical angles. Okay. Now, if you do have more lines intersecting, like something, oh, that was a horrible last line. Let's pretend it went like that. There we go. If we have more lines intersecting, vertical lines are not where we have 3 of them. It's only for 2. So you basically look at this as 2 at a time. So this angle would be vertical with this angle. Okay. This angle over here would be vertical with this one over there. Okay. Now you could, again, just ignoring a line, you could say, well, what about this angle right here? Well, guess what? There are 2 lines. You're looking at this line and this line. Well, the vertical to that would be this one right over here. Okay, so in that case, what we're kind of doing is we're kind of ignoring this line down the middle. We just kind of say, forget that one's there. I don't have to worry about that. So a lot of vertical angle pairs are formed when you have angles like this. But let's take a look. Let's say some of the things we already know. We know certain things make supplementary. And so let's take a look at this. I want to demonstrate why this is such a cool little piece. And it's our first real geometry theorem for the most part. So let's take a look. Okay, so we're going to have 2 lines intersecting. Okay, I'm going to call this just like they did 1, 2, 3, and 4. All right. And so let's see here. So what I do know is I do know some things. Let me change the thickness of this. And I would know that angle 1 and angle 2 are supplementary. Why are they supplementary? Because the line, if we call this one line M goes like this. So when you put another angle like that, those have to add up to 180 degrees. They form a straight line. So we'll just say so, because that's kind of like my, hey, here, that was my reason, and now I'm going to tell you something about it. So that means the measure of angle 1 plus the measure of angle 2 is equal to 180 degrees. Yeah. Okay. Now that's definitely true. Let's go down another line though. Wait, look at this one. There's another line, line N, and it's a straight line. And so that would tell me that angle 2 and angle 3 are supplementary. Okay. Yeah. Which means what? And you can say so, you can say therefore. I guess you could say as a result, we know, but that's just long. So I get used to saying so. And I'm sure I do it in class a lot. That's one of my go-tos when I'm explaining. So anyway, so feel free to make fun of me about it. I know it's there. Everybody has one. That just happens to be mine. So that means angle 2, the measure of angle 2 plus the measure of angle 3 is 180 degrees. Okay. Oh, and as a side note, I'll jot this down here. Sometimes I see students write this, angle 1 plus angle 2 equals 180. There's quite a few things incorrect about this, at least notationally. Now, I think I understand what you mean concept-wise. I think you're trying to say the same thing that I said right up here. Okay, a couple things that you would need to do if you want to get full credit. One, you have to write down the units that you're measuring. It's 180 degrees. Second, without anything else, if you just write angle symbol down, the angle symbol by itself does not tell me that you wanted to know about the measure of the angle. Remember, angle 1 is an object. An object doesn't equal a number, right? The measure of it, when I go and measure how much of an angle is that, that is a number. And so then I would add those together. So what you'll notice is it's missing the measure of, and it's missing the degree symbol. And that's why if you did write that down, you would not get full credit. So get used to writing it. We are very precise in geometry for a reason, and we want to be specific about that. Okay. All right, so let's take a look. So measurement of angle 1 plus measurement of angle 2 equals 180. Measurement of angle 2 plus measurement of angle 3 equals 180, right? Wait a minute. If that's true, if they equal 180 degrees, let me come down here. Then I can use my algebra to say, well, then the measurement of angle 1 has to be 180 degrees minus the measurement of angle 2. Now, see if that makes sense. I'm going to take this object, I'm going to move it to the other side, and anytime I rewrite it, I could rewrite addition as subtraction, or I could say I'm going to subtract something from both sides. You have two different ways to see how I did that. And likewise, look at this one. Let's bring this one down here. Okay, so I'll bring the measurement of angle 2 to the other side as well. So now what I'm saying is the measurement of angle 3 is equal to what? 180 degrees minus the measurement of angle 2. Got it. Got it. Okay. Well, let's take a look. These have equal signs between them. And so if you kind of color code them, and I'm going to color code them here with a little bit thicker pen so you can kind of see a little bit better. So I want you to think about this. Here's kind of blue. Okay. Blue equals green. See green? And down below it, that's the same exact one. So I'll label that as green. And green equals orange. So let's go back to what we've done already in this class. So if we know that A goes to B and B goes to C, if we have a special property, then we know that A has to go to C. And the name of that property is, yes, transitive. And what object do we have here? We have an equal sign. So if A is equal to B and B is equal to C, then A is equal to C. That is the transitive property. And we know that equality is an equivalence relation, which means it is reflexive, symmetric, and transitive. But the one I need right now is transitive. So when we come over to the side, guess what that tells us? That tells us that the measure of angle 1 is equal to the measure of angle 3. Okay. Okay, but look at the graph. Measurement of angle 1 is equal to the measurement of angle 3. So angle 1 is congruent to angle 3. I'll put a little box, and there we go. What did I just prove? I started from just a definition that I know that angle 1 and angle 3 are vertical angles. Then I took what I saw in the picture to be true, which is angle 1 and angle 2 are supplementary. Angle 2 and angle 3 are supplementary. I used that to create some equations, did a small amount of algebra, used our beautiful transitive property to show you that the measure of angle 1 and angle 3 has to be exactly the same. And if it is exactly the same, the angles must be congruent. So I've just shown that vertical angles are congruent. Vertical angles are congruent. Notice I didn't put numbers in here. If I put numbers in here, I've just shown an example, but I didn't put any numbers. I called it the measurement of angle 1. Even if it turned out to be 30 degrees, doesn't matter to me. I've now proved it's true for every set of vertical angles, not just right now, but going on into the future. So that's why when you scroll down a little bit in the book, there's a definition of vertical angles followed by a statement about them saying that vertical angles must be congruent. And we just showed that. So we proved that vertical angles are congruent. Okay. Don't forget, supplementary, we know they have to add up to 180 degrees. In general, so again, if you know the numbers, that's great because you can see the actual numbers. But try to get to a place where it doesn't matter what the numbers are. If one of them was X, the other one has to be 180 minus X in order to add up to 180. Same for complementary. Two things that add up to 90. And again, if you think of one of them as X, the other is 90 minus X. Now, you probably would do this in your head, but if one of them turned out to be 30 degrees, in order to add up to 90, right? The whole thing is 90. If one of them is 30, the other one has to be 60. So you're doing the math in your head. You're doing 90 minus 30 in your head. It's just now, if I don't know what one of them is, I can call it star. The other one is 90 minus star degrees. Okay. All right, let's keep going. So those aren't too bad. Those aren't too bad. Next up, what we have is two lines, two intersecting lines, and then we're going to bring one additional line in. And so what we do is we have a name for it. This line that cuts through and across two additional lines. So if this is M and this is N, the line up here is called the transversal. So it cuts across two distinct lines. All right. Now notice, what do you get with those? Every time you see something like this, you have vertical angles. So like angle 1, and angle 4. So you should be able to look at that picture and say, here's a vertical angle set. Down here also angle 6 and angle 7. Those are vertical angles. You can see where they are on opposite sides. Okay. All right, so now let's take a look. What are these other terms that we have? We have something known as interior angles. And so if you can kind of picture it, think of these lines like here cutting, and they are going to form for us like an interior, like kind of in your mind, what's between the lines, and then go to the outside, like what's outside the lines. And so the outside part will be called exterior, and the inside part we'll call interior. And so that's all we're really doing as we look at these pieces here, okay? We're just seeing, so 1, 2, 7, and 8, those are kind of on the outside. So those are exterior, and 3, 4, 5, and 6, those are the interior angles. Okay, now if you go back to that shape, which would be really nice if it was still on the screen. I know it's on a different page, but what they're going to say is now we have things that are going to be a little bit more descriptive. So let me go ahead and draw that again, and you'll get used to this. This kind of picture happens quite often in mathematics. So whatever we have, 1, 2, 3, 4, 5, 6, 7, 8. Okay, something like this. Okay, so now if you look at it, I don't remember if those are the exact numbers and numbered angles. That's the concept is more important than however they're labeled. So remember, interior angles would be like 3, 4, 5, and 6. Those are interior. But what I want you to do is I want you to look at 4. That's an interior angle, and 5. That's an interior angle. And those are kind of interior angles on the same side of the transversal. But oftentimes in math, we look at ones that are called alternating. So number 4 is on the left side of the transversal, and number 6 is on the other side of the transversal. So that's what we call alternate interior angles. And let's see here. Oh, they did. Oh, shoot. Let me go back and get the exact numbers because they're going to put it this way. Jiminy Christmas. What did I do? 1, 2, 3, 4. Oh, why did they name? They didn't go in a circle. Ah, okay, that's on me. That's on me. All right. Well, we'll fix that. We can fix that. Here we go. Stinking book. Who starts in one way and then changes it up like that? That's a horrible way to do it. 5, 6. Oh, I'm sure they did these then, because that makes a lot of sense. 7, 8. Okay, fine. All right. So here's what we got. 3 and 6 then, wherever the blue dots are, whatever you number them, it doesn't matter. But those would be called alternate interior angles. And so again, there's another pair of them. Again, pick one interior angle and then go to the other pair and go opposite, the opposite side. So 5 and 4. would also be alternate interior angles. And the same thing would be true for exterior, so what's outside. So if I go up here and I say number 2, you can kind of say, okay, that's an exterior angle. So if you kind of trace it down on the same side, you'd get to angle 8, and then you alternate, which means you go to the other side of the transversal. So 2 and 7 are alternate exterior angles. So if you look at the words, they do tell you exactly what you're doing. This is not really something that I feel you end up memorizing. It's something you're just kind of like, oh, alternating, got it. One side, then the other. Exterior, got it. So on the outside, boom, that's honestly what you need. Okay. And then the last thing is what are known as corresponding angles. And so let me just remove some of this so we don't get too many. Oops, I need that back in. There we go. Okay, so let me go here. So now corresponding angles. Now this one may seem a little strange, but I want you to think of it. If I had a kind of a line being cut right here, and I think of this shape, and then I have another line being cut up here, and I think of this shape, we're kind of looking at two things that are both in kind of the lower right, if you think about it that way, lower right. So those kind of correspond in terms of their locations. So if you look at angle 4 up here, it would kind of correspond. If you think of this as a whole, think about where would it correspond to down here, and you'd say, oh, well, that's going to correspond with number 8, kind of in that same location generally. So 4 and 8 are called corresponding angles. Same with 2 and 6, same with 1 and 5, and same with 3 and 7. They all form these corresponding groups. Okay. All right. So there we go. Now, what we get to see in this section, again, 11.3, is we get to see now those transversals. What's interesting is if the angles like 1 and 5 are the same, which we call congruent, then the lines will actually never intersect. Okay. And it's not just true for corresponding angles like 1 and 5, it's also true for alternate interior angles and alternate exterior angles. Okay. And it's also true that if the lines are parallel, then the two angles that are kind of on the same side, not alternating, those had better add up to 180 degrees. Better. And that's how we know things are parallel. All right. All right, so let's take a look at their definition here. If any two distinct coplanar lines are cut by a transversal, then a pair of corresponding angles, alternate interior or alternate exterior angles, are congruent. And here comes the fun part, if and only if. So again, we used that language back in chapter 2. There's a reason why. If and only if the lines are parallel. What does that mean for us? Why is that so important? Because what it says is that it goes both directions. If you know it's parallel, then the angles are congruent. If you know the angles are congruent, then you can prove that it is parallel. Okay. Now, again, this is a theorem. We're not proving it at this point in time. Part of the homework questions will be to prove it, and I can pretty much guarantee you're going to be using this proof on a test. You'll be definitely using the theorem on the test. It could be that someone asks you to prove that this is true. Again, it is a theorem. Theorems are statements that we can actually verify and prove to be true. Right? All right. Now, we'll do an activity in class about this, about the sum of the measures of the angles of a triangle. So I think that'll be a good activity. And I know we get to cut things up and tear them. I don't know. I like stuff like that. I hope you do too. So we'll get to see something like this. And that leads us to a theorem that the sum of the measures of an interior angle of a triangle is a certain number, which is cool. But we're going to actually prove that. So they give a proof here. You will most likely have to prove something like this on a test. But it's really, really good for us to know that fact. Next up, you'll see here in example 6. Notice here it says it uses the symbology. N and M are parallel. That's the two vertical lines. And K is a transversal. And it says, explain why interior angles 1 and 2 are supplementary. Why does 1 and 2, why do the measures add up to 180 degrees? Why is that? And again, you know it's parallel. So remember that theorem that we saw before. If they are parallel, then I know certain angles are congruent. So you get stuff for free, and you could actually go through and use that, especially when you see things are congruent. That's going to be a big one. Okay. All right. There we go. So again, we will have to be able to prove that. Let's see here. The sum of the measures of interior angles on the same side, basically, they make you do it and they turn it into a theorem. Okay. But the theorem is actually a consequence of the parallel lines and alternate interior or corresponding angles. So all of those are true. Next up, we get the sum of the measures of the interior angles of any polygon. Notice this, it's a convex polygon. Okay, we're dealing with convex right now. We'll see later this might hold true for all polygons, but we'll just start with convex. And what we're going to do is, if we can break things up, I mean, look at that, right? It's pretty cool. Break it up into triangles. It might give us a rule that we could use later. Okay, there is a theorem about that. And again, we'll definitely be using that. And then finally, we get the sum of the measures of the exterior angles of a convex n-gon. All right. So we get to see interior and exterior angles of a pentagon. And we get some kind of proof there. Again, another theorem. And then we get to use those. So it's going to ask you to find the measure of things. Oh, don't forget. Now they're going to throw another word in here with regular. So if you know that a triangle, interior angles, right? I got to use, yeah, I guess I'll label them out here. Usually capital letters for points, lowercase letters for angles. Okay. So ABC. So if I say the measure of angle A plus the measure of angle B plus the measure of angle C, and we know that's 180 degrees because that's what's given to us, and we can actually prove that. If we know those equal 180 degrees, and then I tell you that the polygon is regular, remember the definition of regular means all the sides are the same length and all the angles are also congruent. So what you could do is you could say, wait a minute, if all these are congruent and there's 3 of them, then each one must measure 180 divided by 3 if they're all the same. And 180 divided by 3 is 60 degrees. So if you have a regular triangle, this tells you it's going to be 60 degrees for each. And they do the same. They say, what if it was a regular decagon? Well, decagon has 10 sides. So the sum of the interior angles is going to be more than 180, but I just take the total and I divide by 10. Done. So that is the big idea here. Couple of theorems we're going to use. And again, once you get to the homework, and we'll see this as I do my little homework video, but basically you get to do a little bit of problem solving because they'll give you some clues, like they'll give you 2 angles. The question mark is, how can I find the other one? Just remember, for triangles, they got to add up to 180 degrees. So think about your algebraic thinking and just say, what? I got 70, 50 plus 70, and that plus something, question mark, equals 180. That's something you could write as a question mark. You could write it as an X. You could write it as a box. It's up to you. A lot of options exist here. All right. That wraps it up for 11.3. You are ready to roll. Have a great day. Off you go.